My name is Brian Killingsworth. I work with the National Ready-Mixed Concrete Association. As I said, we're going to have 4 different topics today. We're basically starting from kind of the ground up. So we'll talk a little bit about soils and those types of things. As pavement designers, we need to think about, but many times it becomes an afterthought. So we'll talk a little bit about that. Then we'll talk about some of the different design methods available to us for concrete pavement design or cement-based paving design. Talk a little bit about construction and jointing, and then wrap up with concrete overlays for streets and roads. So it's a rehabilitation mechanism for streets and roads. So that's what I'm going to start off with, is talking about soils and local road concrete pavement design. Before we do that, though, I wanted to talk a little bit about the different references that are available to you if you're going to be doing pavement design. So the ACI 325 committee deals with concrete pavement design. We have several different references under that. The ones in green are what we are considered currently up to date. And those deal, there's a guide for construction. There's also one for accelerated techniques for concrete paving. Hold on, sorry. Move that a little bit, make it easier. Then we have one for design. That's the ACI 325-12R, and we're going to be talking about that one primarily today. Most of the information in the first 3 presentations will be kind of covering what's in the 12R report. And then the other one is for proportioning of concrete pavement. So those 3 in green, again, are currently up to date. The 2 in yellow are being updated as we speak and should be going to balloting soon. And then the bottom 2 there are new documents that are being developed. And again, those are moving along and getting to a point to be balloted and published. There are also other committees and documents that I consider kind of fall within that pavement suite of documents that ACI has. And one of those comes from the Pervious Concrete Committee, the 522 committee. It talks about utilizing pervious concrete in paving. We have 2 documents for parking lots and industrial facilities. That's covered under the ACI 330 committee. And then the ACI 327 talks about roller compacted concrete for paving. So those are kind of all the paving references that you might need if you're going to design pavements for various facilities. A couple of these even have specifications, guide specifications that go along with them. So not only just the design side, but also the construction side in terms of a guide specification that you can utilize to go along in conjunction with the design guide. Now, as I mentioned, most of what we're going to be talking about today is covered in the ACI 325-12R, and that specifically deals with the design and construction of streets and local roads. So these are very different than our highway-type facilities that DOTs typically will design. So we're really talking about these lower volume pavements that serve as light residential or residential pavements, collectors, arterials, those types of pavements. That's what we're really focused on today. Now, within the ACI 325R, the design document, it does refer to 3 other documents for various things. There's really good discussion in the construction document, for example, about jointing, about paving, the equipment and things like that. So that document covers construction kind of soup to nuts. When we're talking about mixture proportioning, there's another ACI 325 guide that gets into mixture proportioning and gets in depth with that. And then also there are some things in the ACI 330 industrial guide that are good to refer to, and those are highlighted throughout the ACI 325-12R document. Now, when we talk about a rigid pavement or any pavement, it's made up of consisting of layers, right? So typically in a concrete pavement, We have our existing soil, and then sometimes we'll put a base, or what some people refer to as a subbase, underneath our concrete, and then we have the concrete on top. And one thing that's important to point out is the way that rigid pavement disperses the load as it is being loaded. It's very different than how asphalt disperses load or stress within the pavement. Not saying one is right over the other. It's just a simple fact of the matter is that stress dissolution is different between concrete and asphalt pavements, or what we call rigid pavements and flexible pavements. So what does that mean? Well, that impacts what we need to know about the layers below the pavement. These become a little bit more important because dissolution of that stress is dependent upon these layers here, whereas it's less dependent under a concrete pavement. Now, that is not to say that the soil is not important. What we really stress when we talk about construction and our design and construction of concrete pavements is making sure we have uniform support underneath our slab. One scenario could be where you have a consistent material underneath your pavement, but the center portion of your pavement is compacted to specification. The outer portion is not compacted to specification, so you have a difference in strength. And when you do that, you also have a potential for difference in tensile stress. So the tensile stresses here would be much lower than the tensile stresses here. And when you have that type of situation, you could get longitudinal cracking. The other part of this could be materials management, where we have various types of materials underneath our pavement. And so if we have a kind of a strong material that maybe has some gravel in it, and over here we have materials that aren't quite as strong. When we have different types of materials, you can have that same kind of difference in tensile stresses. And so what we emphasize is making sure that you manage materials properly and the compaction process properly so that you get as uniform and consistent strength underneath your slab as possible. Now, when we are designing concrete pavements, there's 2 or 3 different distresses that we are trying to minimize. One of those being mid-slab transverse cracks. Those are what we consider our fatigue cracks. The other has to do with the joint, and generally what can occur with the joint is joint faulting, where one slab is a little bit higher than the adjoining slab. Okay? That can very many times be a function of erosion that occurs at the joint. So we can get joint faulting because of the dynamics of erosion underneath our joint. And then the other distress that we try to minimize is corner cracking, and that can occur when you have high deflections at the corner of your slab. So these are the types of distresses that we are trying to minimize, and we do that through generally how thick our pavement is, and then also what we have underneath our pavement. Those 2 things become critical when we're trying to minimize those distresses. And this is just a graph here that shows I'm trying to design something that maybe would last 40 years long. If my pavement is too thin, I will meet some sort of distress threshold or criteria, and I won't meet that 40-year design. If I get the sufficient thickness that I'm shooting for, then I will get to that 40-year design and be underneath my distress threshold. So visually, that's what that kind of looks like. Now, thickness design is important, right? That's what we're trying to achieve, is to get sufficient thickness so that we don't get the distresses that I just mentioned there. Doesn't mean that we won't have them, but we keep them at a low threshold. But there's a lot of other things that affect performance of pavement. Your joint spacing, the strength of the concrete that you use, what's going on underneath the pavement becomes important. When we talk about skid resistance and things like that, surface texture is important. Do we dowel across joints? Do we tie joint lanes together? All of those serve a function, a performance function. So it's not just about thickness, but it's also about specifying during construction all of these things that also are important in terms of the overall performance of the pavement. So there's a lot of things that we look at. So obviously the design life, what our traffic loads and frequencies are going to be, all of those are important, concrete strength. But then again, so what we're talking about right here, and what I'm talking about is that support that's underneath the pavement. That also becomes a critical factor in making sure that we meet those performance requirements that we have. There's a lot of other things, again, that we consider in terms of load transfer and controlling uncontrolled cracking, making sure we have good drainage and all that kind of stuff. Those are also important. But I'm going to focus just on the soils portion of it right now. So when we talk about the soils, we have to kind of come to a common agreement about what's important. And we typically do that through a geotechnical engineering report. And so what that geotech report is trying to do is tell us about the suitability of that soil for the conditions that you have, for the environmental conditions and for the traffic loading conditions. So those two things become very critical in determining how thick our pavement needs to be or how it's going to perform. So we do look at the classification of the materials, the native soil that's there. How deep is the bedrock? That's also an important factor. Where's our water table, or how much can it vary from one season to another? And then how does our subgrade compact? We'll talk about compaction a little bit, but this also is an important thing in terms of setting compaction criteria. And do we have weak layers or organics? And then also, is it susceptible to swell from moisture changes or from frost penetration? Those types of things are also important to know. And then what we need for design is right there, and those are our strength characteristics. How strong is my soil? So I have to get some sort of an indication of how well that soil will support our pavement. Now, we can characterize our soil in our subbase, if we have a subbase or a base there. We can characterize that different ways when we talk about strength. We can use what's called a soil support value. That's kind of an old value that was used in the AASHTO design methodology many years ago. We don't really see that used very much anymore, or calculated. Resistance value, or the R value, the CBR, or California bearing ratio, that's one that probably most folks, when they do pavement design, recognize as that CBR value. There's resilient modulus and modulus of subgrade reaction. So we'll talk about those a little bit. But when we're characterizing the soil, we're basically trying to indicate how strong that soil is, right? A lot of times we just do the heel test, right? So we'll just kind of stick our foot down in there and press on it with our heel. And so do we indent it or do we not? You know, is it really strong or is it not? This is a way in which we can get some sort of an engineering value or something that's correlated to an engineering value to tell us how strong that pavement is. So we'll talk about those in just a minute. But we've got to collect data to be able to run those tests that we need, classifications, strength testing, all of that. So we have to be able to get the soil into the laboratory. So the first thing we have to do is design a geotechnical investigation. And we can do that a couple of different ways. It's a function also of, are we going to be doing sampling over a new alignment, or are we going to be doing a rehabilitation design? And so we're on an existing pavement. We need to know information about the existing pavement. So the geotechnical drilling might be slightly different if you're doing a new alignment versus a rehab. But what you want to make sure that you do is go at least 5 feet below the top of the subgrade elevation that comes from the plans. Right? So we know the alignment of the roadway in terms of horizontal and vertical areas. And so we want to try to make sure that we get 5 feet below where that top of subgrade ultimately is going to be. That's for typically low volume streets and roads. That may change if you're doing more port facilities, very high loading type facilities. You might want to go a little bit deeper in terms of your soil drilling. All right? How many times do we actually drill into the soil and take samples? What's the distance between that? That's really a function of the roadway type and the soil conditions. So a light residential street, you may not be taking a whole lot of soil samples. Something like an arterial, you might actually want to do more sampling to get a better idea of the changing nature of your soil. When we have high plasticity soils or soils that can expand and contract a lot, we want to do that drilling depth increase from about 5 feet to about 10 to 15 feet below your top of subgrade. And then in some areas where we need to get a lot of material, you might need to specify a larger auger size to get material to come up so that you can take that to the laboratory. So those are just some of the things to think about when we're asking for a geotechnical investigation. Typically, the geotech report covers these things. It has the boring logs in it, shows the SPT values, and that basically just kind of gives you an indication of the changing layers in terms of its relative strength. We'll describe the materials that we encounter, and we'll do tests where we will get the liquid limit, plastic limit, and PI. We'll talk about that. We'll run density tests, get this percent swell, and then we'll run tests to give us that subgrade strength value. When we classify soils, we typically run a gradation, and then with that gradation, then we can begin to kind of name that soil or describe that soil in ways that we say something like this: sandy gravel with clay, or a high plasticity clay, or something like that. So we classify it using gradation, and then also the soil's ability to take on water. That's what we call our consistency for cohesiveness. And we measure a couple of different things. We generally look at the liquid limit and the plastic limit, and the difference between those two numbers is what we call the plasticity index. So let's talk about that a little bit. We just run these two tests to get the liquid limit, and basically what that tells us is when does the soil change, or how much water does it take for that soil to change from a solid state to a liquid state? All right, so if it takes on a lot of water, that means it can be very cohesive when water's there. And then the other is what we call the plastic limit, and that's the water condition, or the amount of water that it takes for that soil to become cohesive, where it starts sticking together. Okay, again, the difference between that is what we call the plasticity index. If we have very low plasticity index of, say, 3, 4, 5, that's like a sandy material, right? Water doesn't really affect it. If we have a PI value, and I'm from San Antonio, Texas, and if you go east of I-35, you can have PI values that reach 70, 75, even 80. That is a highly, highly plastic soil. And what we have is drought conditions in the summer, so it can find desiccated cracks, large cracks that you'll see. And then when we get to months of like October, lots of rain, and you'll see massive expansion of those soils. It takes on that water, holds onto it, and it just expands to get that volume. All right, so that's plasticity. So there's a couple of different ways we can classify the soil. ASTM has a message, or a methodology. AASHTO has a methodology. They kind of compare in different ways, but basically you look at fine-grained soils, coarse-grained soils, sands, clays, silts, that type of thing. And then you name them with either an A- number, that's the AASHTO designation, or a couple of different letters together, and that helps classify those soils so that we can talk amongst ourselves and understand what that means. Now, one thing that's important also is to know the effect that water has on the soil's density, right? So in a soil sample, we would have solids, we would have air voids, and we'd have water. And that water becomes really important in determining how compact we can get that soil. All right, and so many times what we do is we run what's called the Proctor test, right? Many times you'll hear, what's the Proctor curve? And basically all we're trying to do is determine density of that soil, because when we increase density, what happens to our strength? goes up, generally, right? When we increase density, we increase our soil strength, okay? And it's usually at its greatest, strength is at its greatest at its maximum dry density. So we want to be able to moisture condition to density, which then also tells us what our strength is going to be. There's a couple of different methods that we can utilize to do that, and what those methods do is they change the amount of energy we put into compaction. All right? So highly plastic soils, we might specify standard energy compaction. If we have a base material that has a lot of sand and gravel and things like that, then we might increase the compaction energies to get a little bit higher maximum dry density, which means we can get higher strengths for those soils. All right, when we compact, we're increasing soil strength, but we're also adding water so that we can kind of pre-swell to some degree those highly expansive soils. But what we're trying to do through compaction is get that soil support uniformity that I talked about earlier. And then again, when we compact, we get a stable platform to be able to place the other layers on top, right? If we don't do a very good compaction of the subgrade, and then we put a base on top of that, very difficult then to get our base compacted to where we want it, all right? So trying to get stable layers as we build up. When we talk about soil and base characterization, depending on the design methodology you use, it could be asking for a different subgrade strength characterization. All right, some methodologies may ask you to input the resilient modulus of a soil. Others may ask you to put in the K value. All right, it just depends on the methodology that you're going to use. Some of those testing complex and they can be very expensive, meaning that getting those values from your geotechnical laboratory can be very expensive as well. And then some parameters that are asked for may not be easily determined in the laboratory. All right, and so I talked about these a little bit. These two values, very limited use in the US. Three, we tend to see more being specified and utilized in the US. We talk about the California bearing ratio. Basically what that does is measure kind of the shearing resistance of the soil, and I'll talk about that in a second. Typical values are, 0, that's pretty weak. We generally see a value of 3 up to about 10 for general soils. Bases exceed 10 up to 20 and 25. We talk about resilient modulus. We're talking about an engineering value. Values ranging anywhere from 3,000 up to about 40,000 psi, so a weak clay soil up to a base material. When we talk about K value, we're measuring the resistance of that soil to deflect. And I'll show you a picture that helps understand that a little bit. And we generally see values in the range of about 100 to 200 when we're talking about soils. So the CBR value, this is a setup for a CBR value. You can see we put a soil sample in there that's compacted a standard way, and then we take a piston and we kind of shove that piston into the soil, and we try to determine some sort of a shear resistance, and we can correlate that to strength. That right there is kind of your laboratory heel test, right? That's essentially what you're doing. How hard is it to shove your foot into that soil? You're basically standardizing that and putting it into the laboratory. So just a little bit of background on that there, and you're just trying to see what the resistance is to that penetration of that steel load there, okay? So we've got a standard soil sample, a standard size, and we use a standard rate of penetration, and we kind of record that penetration over time. And obviously the less penetration, then the higher the strength of that CBR. And that's just kind of what it looks like in the laboratory. One thing that's important also is when we run that in the laboratory, we typically put it at its worst moisture condition. So we will saturate the soil sample, run the CBR, and then that gives us essentially what the lowest strength that soil would encounter. And so we utilize that to add a little bit of conservatism typically into our pavement designs. That's a resilient modulus testing machine. Basically, you're putting an axial load and then some sort of confining pressure on it, and then you're putting different types of load onto that soil sample, and you're seeing how it reacts to that load at different stress conditions. And so that gets you essentially a curve of how that soil reacts to different stress conditions. And so it's really considered an engineering property. Okay? And that just shows kind of the setup there. That's a real one right there in this sample that has a sleeve, a rubber sleeve around it. So it's confined, and then you put a confining pressure on your soil and then put an axial load on it. This is the one that we typically use for concrete pavement design. When we're trying to specify what the strength of the soil is, we typically specify the K value. And the K value is nothing more than kind of like a spring constant. So think of the springs on your truck, for example, if you own a truck. Very high, stiff springs, it's very difficult to compress them, right? So that would be a high K value. It's a spring constant. Lower K values, you can compress that spring much easier, all right? And so that's essentially all we're saying with the K value is how tight are those springs, okay? How do we measure that? Well, we put a set of steel plates on top of the subgrade material out in the field that's compacted, and then we put a reaction on it, and we see how much deflection we get, okay? Now, as you can imagine, this is not run very often. We don't normally wait until the subgrade is prepared and constructed for us then to determine how thick our pavement needs to be. So generally what we would do is run a CBR test or a resilient modulus test in the laboratory and then correlate to what the field K value is. Okay? So you will see that in some of the design methodologies, a correlation between a strength parameter in the lab and the K value that's used for design. So again, just kind of practical ranges for these values here. And there are correlation equations that you can utilize to correlate one from another. Now, when we encounter special circumstances, those being areas in which we have frost penetration and heave, and then also swelling of our soils, we need to do some things a little bit differently. We just don't leave the soil in the condition that it's in because we can get issues like this. Now, this is a flexible pavement, but those are typically frozen areas that cause that type of expansion. Believe me, when I was in consulting, dealt with a lot of litigation on expansive soils. They do a lot of damage to roadways, and everybody starts wanting to point the finger when pavements fail before they're supposed to. So litigation is a concern when we talk about expansive soils. So how can we help address some of those things? Well, we can treat the soil with cement or lime or fly ash. We can add geotextiles or geogrids, geosynthetics, those types of things. We can simply remove a portion of that material and replace it with a better material. It's a little expensive to do that, but that can be done as well. For that soil to expand, it has to have what? Water, right? So we can just try to eliminate the water getting into that soil under the pavement, and that could potentially help. So moisture barriers and those types of things can work, but again, kind of expensive. Chemical injection, moisture treatment, soil mixing, things we can do. They don't stop expansion. They just slow it down maybe a little bit or put off the result of that expansion for a few years. You're never going to stop it if you have it. So how do you decide, well, what do I use? There's a lot of different things. It's dependent on the soils and the environment. For example, if you have a lot of sulfates in your soil, it's generally not a good idea to treat with lime. Or if you do, you have to change the way that you put the lime into the soil and mix it and cure it, that type of thing. So the type of soil that you have and the environment that you're in, whether or not you have those sulfates, can you find something like cement, lime, fly ash in your market that you're able to get at a good cost? And also, do you have contractors that have done that type of stabilization in your markets? In Texas, we have all kinds of contractors that are familiar with lime and cement stabilization. In other states, maybe not so much. Will the schedule allow you to be able to treat that soil and let it sit for a week or two? That can be a constraint. So there's a lot of different ways that we have to determine whether or not we can use one of those mitigating strategies. All right, when we're talking about deep soil stabilization, typically what we're talking about is stabilizing the upper 6 to 12 inches. You can go much deeper if you have the right equipment and the amount of time available in your project schedule. But you can do deep soil stabilization if that is one of your options. You can utilize geogrids. I mentioned that before. Typically, I would recommend a triaxial geogrid as opposed to a biaxial type. But there are geogrids that can help kind of lessen the severity of expansive soils. That's just placing it. There's a lot of different things you can do with geogrids. You can place it directly in your subgrade. You can use it as a stiffener to an aggregate base. So there's different places you can put geogrids, but they are effective. And then we can do soil mixing, where we just bring in a lower PI soil and mix it in with the high PI soil. Or again, remove and replace. So there's a lot of different things that you can do to mitigate some of those problems. And then I'll mention one last thing here, and that's full depth reclamation. One of the things that we can do is, if we do have poor soils and we have an existing asphalt pavement, we don't want to necessarily take away that asphalt pavement that's there if we don't have to. So what we can do is mill that material, add some cement to it, utilize it as a strong base, and then put our concrete base on top of it. As long as we can make the elevations work and all of that, we can do what's called full depth reclamation and utilize the existing pavement that's there, that's over and protecting a weak subgrade. Okay, so that is also an option as well. So that covers soil. Do we have any questions, comments, anything that we want to share? Sure. Okay, so you're referring to one of the graphs that I showed that had a distress criteria versus time and a thin and a thick pavement. That right there was just simply a graph to show the concept. So I wasn't looking at fatigue cracking or any of that kind of, it was just simply a distress that kind of accumulates over time. And so that was just simply trying to show the difference between, how if it was too thin, you wouldn't meet your design criteria. So that was all I was looking at there. And then my experience with stabilization techniques. So being from Texas and practicing in Texas for almost 30 years, I've kind of seen it all. What we tend to use in Texas more than anything is stabilization with lime, just because it's at a unit rate that's pretty good. So from a cost standpoint, it works very well. We do, though, have a lot of sulfate issues in some of the Texas soils. So lime becomes a little bit more complicated when you have sulfates, because you can get what's called ectrinite formation, which is a crystal that forms that can just really, really expand and cause issues. When we have those types of soils, you can use fly ash and cement, those types of things.